Hello, everyone. My name is Cole Yarrow, and today I'll be presenting case study 6.1 quality control for variables, focusing on the hub cutting operation at the Whisk Wheel Company. In this presentation, I'm going to be walking through the data collected over 3 production days, the histograms and control charts we created, and the conclusions we can draw about the root causes of variation in this process. So again, this is for the AE 372 final, the wheel whisk hub cutting operation, and the statistical process control analysis, and this will be due December 2nd. This wheel whisk company supplies hubs to several bicycle manufacturers, and they ship them as well. Recently, their largest customer had found that many hubs were arriving late that did not meet their requirements or their length specifications of 3.75 plus or minus 0.005 inches in length specifications. Customers begin sorting the hubs themselves, expensive and inefficient. Wheel whisk wheel must now provide daily statistical data on cutting accuracy, and the goal is to determine the sources of variation and stabilize the cutting processes. These hub shafts are chrome moly steel, cut again at 3.75 inch length. The operator samples 6 hubs every 18 minutes, which gives us subgroups of sizes of 6. The length of each hub is measured, and these measurements are used to form X bar charts, R charts, and histograms. And keep in mind these specification limits are roughly around 3.755 inches as the high and the low as 3.745 inches, and any hub outside of that range would be considered defective. This is the cause and effect diagram. I've decided to go with the fishbone diagram model, and it shows the potential sources of variation. We can classify them into 4 major categories: machines, methods, materials, and operations. Operator factors. Machine factors like maintenance, calibration, tools, wear, and how frequently adjustments are made. Operator factors such as training, supervision, and importantly, over adjusting the machine. Some methods would be including the jig design, cutting technique, and tooling setup. And then material, we're going to go with raw steel variation and mechanical properties. And these categories will help us understand the process and guide our investigation into variation. This is the day 1 histogram. What immediately stands out is the bimodal distribution, meaning the data cluster around 2 different centers. So the bimodal shape is a strong indicator that someone is adjusting the machine frequently, creating 2 different operating settings within the same day, and this is known as tampering in statistical quality control. We also see several values beyond the specification limits, and you can see the values outside the specification limits on both sides have a little extra. The process is not capable and is not in control. There is clear signs of special cause variation introduced by the operator. And so overall, day 1 shows the process is not in control and not capable of meeting customer specifications. Day 2 histogram looks slightly better, but still contains a wide variation, and some values are still outside of the spec limits. This again suggests that the operator is adjusting this process too often, and this distribution is still not stable, and the process remains incapable. It's slightly less bimodal than the last one. Still excessive variations, and several values are still outside the specs, like I just said, and the operator continues making adjustments throughout the day. So, and then what we see from this so far is that the problem is more likely not the machine itself, but how the machine is being operated by the operator. This is the day 3 histogram. On day 3, the operator was specifically instructed not to make any adjustments during the entire day. This histogram becomes much closer to normal distribution with far less points approach spec limits. This indicates that formal removal of operator created special causes. and the variation was significantly reduced. And so this alone tells us something extremely important. When adjustments stop, the process becomes naturally stable. In other words, the operator's actions were the primary source of this variation problem. Now we're about to go over the X chart. This X chart uses the control limits from the first 2 days, which were calculated earlier. When we plot the day 3 averages onto those same limits, we see that almost all subgroup means fall comfortably within them. There are no patterns or trends indicating instability. Nearly the processes mean it is more stable with less drift. And the major conclusion, the lack of tampering leads to stable averages. So this chart confirms the histogram story. The process means stay stable when the operator stops tampering with the equipment. This slide is day 3 of the R chart. This R chart shows the variations within each subgroup. The UCL was equal to 0.018268, and the LCL is 0, which all points were well within those limits. This indicates that the internal spread of the process is consistent and predictable, and it is consistent with the variation. There's no evidence of special cause and variation on day 3 spread. The R chart stability, which is equal to a strong evidence of an in control process. So this means that the stable R chart is a sign of true common cause variation, exactly what we wanted to see in a controlled process. Based on the day 1 and day 2 histograms, they do not meet the specifications, which means the process was not capable, again, of meeting the specifications. Too many values fell outside of the range of 3.75 plus or minus 0.005, which is 3.755 or 3.745 of the range. Day 3 improved significantly, but capability depends on both centering and variations. As long as the operator avoids unnecessary adjustments to the process, then we can move forward towards capability. And so to confirm the full capability, we estimated sigma and z calculations, and that would be used to estimate the percentage above and below the spec. So the clear message, stability must come before capability. And again, to quantify capability, we would use the estimated sigma and z values to calculate the percentage of parts above and below the specification limits. After reviewing the process and observing the operator, we found the true source of variation: over adjustment or over control. Each adjustment increases the variation, which we know as tampering. If the operator stops the machine, loosens clamps, jogs the tool back and forth, and then restarts it, this takes several minutes and it would still throw off the process. The cutting process. Instead of letting the natural process variation occur, the operator reacts to individual measurements and tries to fix each one of them. This creates special cause variation on top of normal variation, leading to instability, wasted time, and inconsistent product lengths. Again, adjustments could take 5 to 10 minutes, and which is time lost of making the parts and causing more problems with them. Then when he stops doing it, it makes it a lot better for us, quicker, we can get more parts through and less problems with it. So the key finding was the operator, not the machine, was creating the simple variation. This is the recommendations. Based on the analysis that I can recommend the following. You can stop unnecessary adjustments, let the process run naturally unless a true special cause occurs. You can implement SPC charts so that the operator understands what the signals mean and when the action is needed. You can provide training on common calls versus special calls variation. Number 4, you could standardize tooling and jig setups to reduce method-related variations. And then number 5, you can continue using day 3 as the new baseline for stable process behavior. These recommendations help Whisk Wheel shift from a detect and sort kind of approach to a true process control. The summary. To summarize, day 1 and 2 showed unstable, high variation due to operator tampering. Day 3 was dramatically more stable, confirming that the operator was the source of the variation. Control charts supported the findings from the histograms from the 1, 2, and 3-day histograms. With proper training and SPC implementation, this process can become both stable and capable. This case study demonstrates how data and control charts reveal the true behavior of a process and how the human adjustments can unintentionally introduce variations even without trying. Thank you for listening.